Okay, so good afternoon and welcome to the Scripps Technical Forum. I am Douglas Alden. I'm a research and development engineer with the Center for Western Weather and Water Extremes here at Scripps. In addition, I function as the STF chair and get assistance setting up and running STF from my colleagues here on campus, Gwen Nero and Vanessa Scott. Gwen is Director of Corporate Affiliates, Business Development, Industry Outreach and Innovation, and Vanessa is an Industry Relations and Innovation Analyst. And if you've missed any of our recent presentations, you can find them on the Scripps Technical Forum playlist on the Scripps Oceanography YouTube channel. We've been, ever since we've come onto this virtual format, we've been recording them, so you can find them there. And you can either go to the YouTube or you can go to the stf.ucsd.edu website and look at past presentations, and there's a link to all the webinars. And with that in mind, please know that today's presentation is being recorded. You've all been muted when you logged into the conference. If you have a question for one of the, or for the presenter, please use the Q&A function, or you can unmute. And today we're gonna have a presentation by Dr. Bruce Armstrong from GeoSpectrum Technologies on the physics of pressure hydrophones, omnis, and the relevance to practical use. Bruce has a PhD in plasma physics, 42 plus years of experience designing underwater sound transducers, first as a defense scientist, later as a sonobuoy company designing vector hydrophones, and finally as the founder of GeoSpectrum Technologies Incorporated. And I also want to add, I just want to thank all of you that responded with questions in the RSVP for today's meeting. It's a new part of the format we're trying out, and I'm hoping to engage the community and foster a broader discussion. And with that, I'll hand it off to Bruce.
Thank you, Douglas. Okay. No, I'm not seeing, oh, there we go. Good afternoon. My name's Bruce Armstrong. I'm really delighted to be here. I've been doing underwater transducers for 42 years, and I'm really happy to be able to pass some of that knowledge along. GeoSpectrum is a designer of sonar systems and all the bits that go into them. We're located in Dartmouth, Nova Scotia, Canada, so you can see us off there in the Atlantic Ocean, and in fact, GeoSpectrum is right on Halifax Harbor, Bedford Basin, and that's where we do a lot of our
Bruce,
Yeah.
Bruce, I'm just sorry to interrupt, but I think that if you're showing slides, they haven't. You've got to share your screen. Yeah.
Okay. Just a sec here. One moment, please. Thanks.
Yeah. No worries.
Okay, sorry. It's going to take us a moment.
I can't hear.
Oh. How's that?
That looks great.
Okay, perfect. Okay, so GeoSpectrum is on the Atlantic Ocean on the eastern seaboard. We're right on Halifax Harbor, so we do our calibrations of low frequency stuff in the harbor. I'm going to be talking mostly about pressure hydrophones. Thanks for all your questions. I have incorporated the answers to those questions mostly in the main body, but there were a couple of submitted questions that aren't in the main body, so my answers to those things will occur at the end of the talk. So mainly I'm just going to tell you how pressure hydrophones work and how you can use them perhaps better than you are now. So pressure hydrophones are, I show a simple one here. You take a piezoelectric ceramic tube, you wire it, you put wires on the inside and the outside, you seal the ends with end caps, and then you put a bit of waterproofing around it. And that is your simplest hydrophone. So pressure creates axial and circumferential stress in the ceramic tube. That ceramic tube with the stress in it creates electrical charge. And the construction of hydrophones, you always try to minimize some of the stresses in it. In this case, you have to minimize the radial stress, and that's why hydrophones have air inside them. If you did not have air inside the hydrophone, then you wouldn't have much of a hydrophone. Other shapes are possible and quite common. I've just showed you one of the simplest. So the one thing that you really need to know is that hydrophones are stress gauges. That's all they are. If you put stress into the ceramic, you're going to get a charge out of that ceramic that's proportional to the stress. So it's a linear device. The acoustic pressure creates a desirable stress. That's the signal you're looking for. And everything else creates undesirable stress. So if you have any mechanism that is stressing the ceramic doesn't know that it's not acoustic, and it's just going to generate charge and you get noise. So if you're building arrays, you're going to get horizontal mechanical force coupling. If you're accelerating your hydrophone, it makes noise. If you're going up and down in the water column, it senses the pressure change. If you're near the surface and there are waves, you will feel the effect of the waves. So anything that creates a force creates an output. So one question that was asked was, what determines the depth limit of a hydrophone? Now, depth limit is determined by the crush depth. If you don't break it, it's still going to work. And if you want more depth, you just have to increase the wall thicknesses of some components. That comes at a price of more low-frequency electrical noise, mind you. And the ceramics are actually quite amazing. You can go to full ocean depth, so that's 10 to the 8th pascals, and you can still be measuring pressures of 10 to the minus 4 pascals, or even less. So that's 12 orders of magnitude different. Now, I'm going to start talking about in-water calibrations and the substitution method. This is what most people use to calibrate hydrophones. And they use it because it gives you the shape of the response curve. So you need to do in-water calibrations for at least part of the time. But then after I finish talking about this, there's another method that you can use to calibrate hydrophones at low frequencies. And that's the one that'll be useful, I hope, to many of you. So the way that you calibrate a hydrophone normally is you put both in the water, that's as deep of water as you can find. You energize a sound source to produce usually a tone. You measure the sound pressure level with a reference hydrophone, and you store all the sound pressure levels that you've measured. And then you repeat that for multiple frequencies. Then you remove the reference hydrophone, you substitute the unknown hydrophone in the same location, and then you re-energize the sound source in the same way that you did on your reference run. And then you just compare your unknown outputs to the stored values from the reference, and you have a sensitivity curve versus frequency. One little wrinkle is that you want to measure the received sensitivity, the hydrophone, without complications from reflected energy. So the depth of your calibration determines how low in frequency you can go. You know, there's a little transit time from the source to the receiver, and then there's a longer transit time from the source to the water surface and back down again. And the difference in those times is a maximum measurement window, so that determines the low frequency limit. And if you do a really good job, you can get plus or minus 1 dB accuracy. If you don't do a good job, you can be considerably worse than that. So this slide shows that there are two frequency regimes in a hydrophone. There's the high frequency regime, and in that, it must be calibrated in water to get a calibration there. And in the high frequency regime, the hydrophone size is comparable to a wavelength. And that really means that the pressure is not uniform on the hydrophone surface. So you're getting diffraction effects. And also, the high frequency regime occurs when you get near the hydrophone resonance. It's a mechanical structure. it'll have one or more mechanical resonances. And when you get near those, you also have to calibrate in water. But then you get the low frequency regime, and that's where you can do your calibrations in air if you wish. And you see the low frequency regime is characterized by that ruler flat response from, I graphed it here from 1 hertz, but it goes down to 0.1 hertz or 0.01 hertz, all the way up to, in this case, about 10 kilohertz. So in the LF regime, the hydrophone size is far smaller than a wavelength, and what that means is that the pressure is uniform around the hydrophone. All parts of the hydrophone see the same pressure. And the frequency is also far below a resonance. What that means is that the mass of any component in the hydrophone or the water is not important. The forces required to stress the ceramic are completely controlled by the stiffness of the ceramic, and there are no inertial effects. So if you're down at the low end of the LF regime, you can calibrate in any fluid that applies a uniform pressure. And here is the essence of how you do it. I'll show you some real life examples. But what you need is a reference hydrophone. You need a container that's sealed, more or less. It doesn't have to be perfectly sealed. You need a means to create a continuous wave dynamic pressure within the container at a low frequency. And you need a means to compare the outputs of the reference and unknown phones. So the technique is you put the phones in the container, and the position of them is not important. You energize the sound source and you compare their outputs, and you do this with continuous sound. Inside the sealed box, there's isotropic dynamic pressure. In other words, the pressure does not vary with position in the box because you're at a very low frequency, and you're pressurizing the air in the box, and that air impacts the unknown phone and the reference phone in exactly the same way. So you get the pressure sensitivity of your unknown phone. Now the magic of, let me talk about this first. With the sealed box, you get really accurate calibrations, and the reason they're accurate, well, there's many reasons. I won't go into them. It's hard to make a mistake. In water, it's easy to make a mistake. And it's a really convenient way to calibrate hydrophones at low frequencies. The secret sauce to all of this is the reference phone that you can use for measurements. I've shown here a bidirectional differential pressure transducer. These things are meant to measure static pressure, and you can get them a traceable calibration for these when you buy them. The accuracy of good ones is better than 0.1%. So now you have a reference phone that's accurate to 0.01 dB or a little better than that. You can't get that with the normal hydrophones that you buy or rent from manufacturers. Now, the pressure transmitter is calibrated with static pressure, but it still works at low frequencies. It's got a resonance of 1 or 2 kilohertz, so you can use it at 1 hertz or 10 hertz or 100 hertz, it's fine. If you got up to 1 or 2 kilohertz, it would not be fine. So the way you use it is that you put the dynamic pressure inside the box on one port, and you seal the other port by some means. And an example of sensitivity is you can buy a pressure transducer like this with many different sensitivities. But if you buy one that's 10 volts per bar, that's 10 to the minus 10 volts per micropascal, which is a minus 200 dBV Ray a micropascal hydrophone. And once you've calibrated, once you've got your calibration system set up with a pressure transducer, you can calibrate any piezoelectric hydrophone you have, and then you can use it as a reference if you want to quit using your pressure transducer. So here is your budget calibration system, and this is actually one that we use. It looks crappy, but it works just fine, and you make it out of a sewer pipe. So you've got a length of sewer pipe, you've got some rubber unions that join sewer caps. At one end of the sewer pipe, you have a dynamic pressure inlet, And at the other, you have some wires that you pass your signal leads out of the sewer pipe. And if you take a speaker and put a piece of plywood on the front of it and connect it to the dynamic pressure inlet, now you've got a sound source. So you just take some signal generation, pass it through an audio power amplifier, and drive the speaker. That produces pressure that enters the piece of sewer pipe. And then you've got a perfectly fine calibrator. The only expensive part about this system is the pressure transmitter, which is typically about $1,000. Here's an example of an expensive system, same principle, but this one was designed to put some static pressure on the hydrophones during the measurement. And it was also designed to produce an extremely high dynamic pressure. This was producing something like 210 dB, but you can make measurements at whatever frequency you want, down to less than 0.1 of a hertz if you have a sound source that works there. The sealed container in this case is machined out of metal. It has a bulkhead connector to get signals out. It's got a pressure transmitter fastened into the side as a reference transmitter, reference hydrophone. And it's got that big blue tub with a very large subwoofer in it to generate pressure. And you can see a folded pipe in the picture. That is just a means to create a resonance to amplify the amount of pressure produced by the speaker. You don't need that. Here's the same technique, but in this case you do it in water. I've been talking about air, but this technique works in water just as well. So here's a pressure vessel that has a 13-inch internal size, and it takes 150 bar. There's a piezoelectric source in the bottom, and you again use a differential pressure gauge as a reference. So now you can calibrate hydrophones as a function of pressure down to the limit of the pressure vessel. And the good thing is the reference hydrophone is temperature compensated, so you can do this at whatever temperature you wish as well. GeoSpectrum makes an automated version of a calibrator. So this one's computer controlled, and it's meant as a field calibrator. A lot of this equipment was designed for the seismic industry. And in this case, the hydrophone that it calibrates has an EEPROM built into it. So every time you calibrate the hydrophone with this calibrator, it writes the calibration data and the dates and the capacitance into the EEPROM. So if then a customer is looking for, if you have an NIST traceable hydrophone, all the data will be contained within the hydrophone. You can use this technique to calibrate arrays. So here's, you've got a case where the box isn't perfectly sealed. You machine a metal box, and you've got some rubber seals where it goes around the cable. It's not important whether you get small leaks, because you're measuring the unknown hydrophone and the reference hydrophone at the same time. So a small leak just creates a slightly lower dynamic pressure. So what can you use for voltage measuring? If you're really on a budget, you can use a multimeter. You can use an oscilloscope, going upscale a bit. You can use a DAC and MATLAB. But my favorite is to use a spectrum analyzer that works from DC and up. So you drive your sound source with white noise. You perform a transfer function between the reference phone and the unknown. And that's just really comparing things as a function of frequency. And then you look for a flat line response. And if you get a flat line response from your transfer function, you know you're making a good measurement. Because if you recall back to the calibration curve that you saw for a hydrophone, it should be flat at low frequencies. So if I'm measuring a hydrophone at 1 hertz or 5 hertz or 10 hertz, it should be the same number. The one little caution is that piezoelectric hydrophones will roll off if they're driving a low impedance, and most of these things are 1 mega impedance. So if you have a normal hydrophone, you're going to have to put a high impedance preamp in there to stop it from rolling off. Either that, or you collect the data and analytically correct for the roll-off that's occurred. So another question was, how low a frequency can you go? And the answer is as low as your source of dynamic pressure. Now, if you're using a speaker for your source of pressure, I don't know if speakers are airtight at 0.01 hertz, for example. And so if you've got an air leak that's significant over your 100-second period, then you wouldn't get much pressure out of your speaker. But the neat thing is, you don't have to have a low distortion source if you're producing a transfer function. So if you had a sealed container, you could just take a bladder and squeeze it by hand, and you would create a complex spectrum that your spectrum analyzer would sort out for you, and you'd still get a transfer, or you'd get your accurate calibration down to whatever frequency that you choose to use it at. Okay, new topic, acceleration canceling. Now, you saw the previous hydrophone I showed you was a piezoelectric ceramic cylinder with a couple end caps. So if you want to make that hydrophone be acceleration canceling in a traditional method, you can have two ceramics. You have a central mount, you put a ceramic tube on either side, and you wire the ceramics in parallel. Now, the key to the approach that I'm about to explain is symmetry. You want to build a symmetrical hydrophone. So let's apply an axial force to the central mount. So that force accelerates the hydrophone, and that acceleration produces force in the ceramic. So you get a compressive force in the upper ceramic, you get a tension in the lower ceramic. So those forces are creating electrical charge, but because you're creating compression in one ceramic and tension in the other, the charges are of opposite polarity. So if your top and bottom tubes are identical, the charges add to zero. So you can't stop the acceleration forces from creating charges, but what you can do is arrange your chunks of ceramic so that the charges add to zero somehow. And this is what I've just shown here is a traditional way of doing it. There are others, but this is the simplest one to visualize. So the summation of this, or here's an example of, you can take an acceleration canceling hydrophone and you can actually make it non-acceleration canceling if you put the force in the wrong place. So take the same phone, if you put the force on the bottom of the hydrophone rather than on the central mount, both ceramics go into compression, and then your charges don't add to zero. So just because you've purchased an acceleration canceling hydrophone, you still have to mount it properly in order for it to work as intended. So when do you actually need an acceleration canceling hydrophone? Well, probably the biggest place that you need them is when you're towing an array. So if you have a horizontal line array and you're towing it, there's some tension in the tow cable. That tension is mostly DC or static, but there's always some fluctuating components, some dynamic components. Those components accelerate the array, and the hydrophones pick up the acceleration. So if you're doing a seismic survey, which goes down to 3 hertz, you really need acceleration canceling hydrophones. Otherwise, you'd get a pretty useless array. You sometimes need them in vertical arrays. So if you have a vertical array with a surface expression, then you're putting some force onto the vertical array, and that force is going to couple to the hydrophones and accelerate them. But in this case, you can also, the force in the vertical array can also increase the height of the hydrophone or change the depth. And that depth change is a pressure change, and that also shows up as noise. So whether you need an acceleration canceling hydrophone really depends on the frequencies that you're looking at. At low frequencies, you don't need it. At high frequencies, you do. One of the common methods, and this is, I'll promise to teach you a little bit how to make arrays. One of your biggest sources of noise is coupling to the strength member in your array. if you look at your strength member, it's got newtons or thousands of newtons in the strength member. And some of that is dynamic. It's not a static force. It's got fluctuations in it. That causes the strength member to stretch and contract. If you look at the forces you're getting in your hydrophone, it's measured in piconewtons from the acoustic pressure. So you've got, kilonewtons in your strength member, you've got piconewtons in your hydrophone. And so if you do not decouple the strength member from the hydrophone, you will have a noise problem. So my advice to you is to go absolutely overboard to reduce the coupling. In a vertical array, what you want to do is have a strength member, a cage, and then the other part of your strength member, and you put the hydrophone inside the cage, and all your forces from the strength member go through your cage, and your hydrophone is just hanging. That's a successful technique that is proven to work. So the next topic is, what is the low frequency limit of a hydrophone? So if I show you this calibration curve, I could have written it down to 0.01 hertz if I wanted. Is that a 0.01 hertz hydrophone? The answer depends on how loud the sounds are that you're listening to. The hydrophone will operate properly at 0.01 hertz, but is that going to be of any use to you? And the answer is, it depends on the noise in your preamp. So what you've got plotted in front of you now is the electrical noise of a preamp plotted in SPL equivalent. So in the high frequencies, the voltage sensitivity of the hydrophone determines the high frequency noise, and the charge sensitivity of the hydrophone dominates the low frequency noise. Charge sensitivity being a product of the capacitance, i.e. how much charge you have, and the frequency. So in this case, 1 nanofarad hydrophone with a sensitivity of -200 dB has a noise curve that looks like that. So if I build a hydrophone with more capacitance, now you can see a different noise curve for those. And I guess the dotted part curve went away, but the lower noise curve is the 64 nanofarad one. And now you get the same voltage noise at high frequencies, but you reduced your low frequency noise. If you do a combination of, say, 8 nanofarads and a -190 hydrophone, now you lower your high frequency noise, which was voltage controlled, and you lower your low frequency noise as well. So I've shown you that extra voltage sensitivity and extra capacitance lose noise. So why don't you always make hydrophones with a high voltage sensitivity and high capacitance? The answer is you have to give something up. Every time I increase the voltage sensitivity or capacitance, I'm subtracting from some other attribute of the hydrophone. So really, the question is, what are you willing to give up for lower noise at low frequencies? The ceramic depends, or the capacitance depends on the ceramic wall thickness and its length. So if I decrease the wall thickness of the ceramic, I get extra capacitance. But what I'm giving up is depth capability. With a thinner wall, I will break I'll crush it at a lesser depth. There's a limit to how thin manufacturers can make ceramics anyway. And so most hydrophones are made with a pretty thin ceramic. So making it thinner is not a feasible approach. You can increase the length of the ceramic, that's feasible, but that sacrifices your high frequency response. You're going to have a lower resonance in your hydrophone, and you're going to get more directivity out of your hydrophone. You can increase the voltage sensitivity by increasing the diameter of the ceramic. But if you do that, your increased diameter sacrifices high frequency response. You get a lower resonance, you have a bigger hydrophone, and so you have diffraction effects sooner. You can play games with your electrodes and split the electrode and wire things in series, and then you lose capacitance. And so that increases your low frequency noise. So even though my previous hydrophone that went down to 1 hertz works perfectly fine at 1 hertz, it's not a particularly good phone because I don't have enough capacitance. So let's look at hydrophones as energy harvesters. And you'll see why high frequencies and low frequencies are in competition with one another. Hydrophones harvest acoustic energy and they produce electricity from that little harvest. So the force from the acoustic pressure deforms the ceramic. So the force times the displacement of the ceramic is the amount of work that you've done. Some fraction of that work shows up as electrical energy, and more electrical energy shows up as either more voltage or more capacitance or both. So let's look at a hydrophone of a certain size. The energy that it harvests is 1/2 times its capacitance times the voltage squared that it generates. Now, if I take that hydrophone and I double all dimensions, so now I've got 8 times the amount of piezoelectric material, I half the resonance frequency, I double the voltage, and I double the capacitance. So now the energy is 8 times as much as I had in the original hydrophone. So if I make my hydrophone twice as big, which is 8 times the amount of active material, now I've got 8 times the energy. So now I've got a better hydrophone at low frequencies and at high frequencies for that matter. And so you can see that the high frequency performance of a hydrophone and the low frequency performance compete with one another. If you want a hydrophone that works out to 200 kilohertz, you have to be willing to give up low frequency performance. You just can't get it. That high frequency hydrophone has to be small to operate at high frequencies. And when it's small, it doesn't harvest very much energy. Okay, now one of the questions that was asked of me was, what do I see for MEMS and other sort of non-standard technology? I got to put a disclaimer in here. I've got zero first-hand knowledge of MEMS used as hydrophones. But if you refer back to the previous discussion, MEMS are small, and small things don't harvest very much energy. So you're only going to be able to use them when you have a fairly loud sound, because you're going to have an electronic noise floor that masks everything else. Or if you make the MEMS really soft so that it harvests more energy, you're going to sacrifice survival depth. Another technology that is being used is fiber optic hydrophones. And these are pretty specialized hydrophones. But the only time you use them is if, say, you wanted to create a surveillance array that was 10 kilometers off your shore. A 10-kilometer cable putting power out to your system is pretty expensive. So what you'd rather do is have your hydrophones out in the water and have all your equipment on shore. And the way to do that is with fiber optic hydrophones. But that's one of the few cases where fiber optic hydrophones are useful. So one more question, one more question that was asked about vector hydrophones. And so what I'm going to very quickly address is, what are they, how do they work, how do you calibrate them, and how do you interpret their output? This subject should be a complete webinar topic. It's nothing I can do justice to with just a few slides. But the difference between what we have been talking about and vector hydrophones is that vector hydrophones are designed to respond to pressure gradient, whereas previously what we've just been talking about, they respond to pressure. So let's look at one type of vector hydrophone, and that's an accelerometer-based vector hydrophone. What it is you have a pressure vessel. Inside the pressure vessel, you have a rigid mount, and in that mount, you have accelerometers arranged at right angles to one another. So you could have X, Y accelerometers, or you could add the Z direction as well. For you American folks, I said Z rather than Z. And you put some electronics in there, and you put a compass in there. And so a pressure wave passing a hydrophone produces a pressure gradient. That pressure gradient accelerates the pressure vessel, and your accelerometers have to be sensitive enough to pick up the movement of the pressure vessel. but you're talking incredibly small displacements. The best vector hydrophones will pick up noises of 80 dB or a micropascal at 5 hertz. If you do a calculation, that ends up being a displacement of the pressure vessel of 2 times 10 to the minus 10 meters. And just to put that in context, that's 3 times the displacement or distance between the electron and proton in a hydrogen atom. So that's an incredibly small displacement. And the lesson you should take away from that is that vector hydrophones have high mechanical noise at low frequencies compared to pressure hydrophones. The beam pattern of a vector hydrophone looks like this. So you've got the X and Y channels. Those are cosine patterns. So you have a maximum along one axis, and at 90 degrees to it, you have a minimum. And you have 2 channels. So you have an X and Y channel in this case. And the null depth should be at least 20 dB. And this pattern should be independent of frequency. At 5 hertz, you should be getting the same pattern as you do at 2 or 3 kilohertz. In a vector hydrophone, you also have a pressure hydrophone, the one that we've been talking about, and its pattern is omnidirectional, which is why they're sometimes called omnis. These are the lengths you have to do to calibrate these things in water. You calibrate them in the same way as your pressure hydrophone, except that there's a complication. You must apply a near field correction. That's because these are responding to pressure gradient. And when you're near a sound source, there's an extra component of pressure gradient that doesn't matter to a pressure hydrophone. And this is what a calibration curve looks like for a pressure hydrophone. A pressure hydrophone, you see the omni, labeled omni there, that's your pressure hydrophone. It has a flat response. The vector hydrophone, the XY channels, have a response that rises at 6 dB per octave, reaches a peak, and then falls at 6 dB per octave. So vector hydrophones respond to pressure gradient, not pressure. But we reference the output of a vector hydrophone according to pressure. So why do we do that? Well, one answer is it's convenient. But looking a little deeper, looking under the hood, the sensitivity is being referenced to the pressure gradient that is produced by a plane wave pressure. So it's not responding to the pressure. I plotted it versus pressure. It's responding to the pressure gradient. And if that pressure gradient is created by a plane wave, then I can calculate particle velocity from that. So you use vector hydrophones when you're not measuring a plane wave, and then you can use them to get particle velocity. This is what the accelerometers in a vector hydrophone could look like. It's what they look like in some of ours. You can also show them calibrated on a shaker table here because there's a relationship between acceleration sensitivity and hydrophone sensitivity. And so you can actually just calibrate these in the lab on a shaker table. Anyway, that is all for the formal presentation. I'm happy to answer any questions.
So far, I haven't seen anything up on the Q&A, but if anyone wants to unmute and ask a question using the microphone, please go ahead. And if there are no further questions this time, we also have Matt Jetsu, who's a research geophysicist with IGBP here at Scripps, who's going to share a slide and talk a little bit about his experiences.
Hi, everybody. Bruce, I had just one question. You talked about acceleration canceling hydrophones in the vertical. Is there a way to do it in all directions? It's just more complicated.
No, they're inherently balanced in 2 directions. If you take that symmetrical tube hydrophone that I showed, and if you shake it in a radial direction, your ceramic tube cantilevers, one side of your ceramic is going into tension, one's going into compression. So the ceramics automatically cancel in the radial direction. So the only thing, you only have to cancel sensitivity in one direction. So that's why you use a symmetrical construction.
Oh, okay.
So you get two of them for free, two directions for free.
Oh, good. I didn't know that.
Yeah.
All right. So uh, Doug asked me to say a couple words about our experience with Bruce and GTI. And so this is kind of at the other end of the spectrum. Not only do they not only does GTI make hydrophones that can measure very small sounds in water, they also produce sound sources that can produce loud, very loud sounds in water. And so this is the one of the two sources we bought from Bruce's company last year, and we used it to we deployed it in the Arctic last year, and you can see it here. I think you guys can see my screen. Yes.
Yes.
And
Yes,
the sound source is actually right here. Well, I don't know if you can see me pointing. Maybe you can't see that, but it's the round drum-looking thing on the lower right side inside that cage. And Bruce can talk about the construction if I get it wrong, but I think it's driven by some electric motors inside, and it's basically a big drum, and it pushes that drum back and forth and produces, or the plates of the drum back and forth, and produces this one. This one particularly produces sound at 35 hertz at about 196 dB. And the other components that are in this cage are there's 3 air bottles up above there. They're the pressure compensation, because there's air inside the drum, and it needs, as you lower it to a depth that you have to compensate the static pressure. And then there's a couple other tubes there, the battery packs, and you can't see the electronics package and the power amplifier there in the back of this picture. But we deployed this last year at about 60 meters depth. This one was in the Beaufort Sea. There was another one in the near Svalbard. So we transmitted back and forth across the Arctic, and I'm happy to report that both, I think we have receptions from both almost the entire year, I think, that they were deployed. So we haven't recovered all the gear yet, but the gear that we did recover so far from the Norwegian side of the Arctic has receptions from both sound sources all year long. So we think that it's obvious that they did work all year long. So congratulations to Bruce for building this for us. I think it's going to be a big success when we finally get all the data back and are able to analyze it. So.
Yeah, well, thanks, Matt. We were relieved to see that they had operated all year. This was a good cooperation between Scripps and GeoSpectrum. GeoSpectrum built half the equipment. Scripps built the other half. It was all shipped to GeoSpectrum for integration, and Matt and Peter Worcester, oh, can't get that name, sorry, Matt, came up here, and we calibrated it in Bedford Basin because we have 60 meters depth there. So we were able to test the complete system here, and we shipped them off just in time to make the icebreaker sailing.
it's great. Well, thank you, Matt, for sharing that and your own personal experiences there.
Sure, you're welcome.
So with that, I just want to let everybody know, well, I want to thank Bruce and Matt both for their time today. It's been a great presentation. I definitely learned. Oh, we got another, before I finish up, we've got one question from Ryan. It says, does GeoSpectrum have any good ways of isolating velocity sensors from structural vibrations in a cabled array?
No, I'm sorry to say. Our hydrophones, the XY channels of our directional hydrophones have a noise canceling feature that will take out the low frequency noise to about a level of 20 dB, less than you'd normally get. But there is no easy way to decouple. I used to design sonobuoys, and in that case, we had 100 feet of suspension that was designed to isolate from surface motion. But even then, you could see the effects of surface motion. And so you're measuring displacements that are so tiny, you just can't really decouple easily from them. You just have to put up with the noise at low frequencies. It's a big challenge with no good answer.
Thank you, Bruce. Thank you again, Bruce. So just to let everybody know, in October, we're going to have Turner Designs, who's a maker of submersible fluorometers and sensors. And then in November, Okika Technologies, who is putting together field programmable analog arrays, which have probably some use with transducers here, because you can do all sorts of creative things with that. So hope you guys will turn in. And as always, we welcome input from the community. So please let us know if there's a subject that you want covered, or if you have a technology that you're working on in your lab that you'd like to present on. With that, thank you everyone for attending today.